So I'm Martin, and today I'm going to tell you about a line of work we've been working on at ETH for the last 5-6 years on making machine learning models more provable, more safe, more reliable, more fair, more secure, with ultimately probably the differential is the mathematical guarantees, that you get some mathematical guarantees out of those constructions that you're going to see today. Okay, so let's just see if it works here. Oops, it's not triggered. Okay. So what I'm going to talk about today is joint work with several students at ETH Zurich in the group, Mislav Balunovic, Ani and Rus, who is now at DeepMind, Momchil Vechev, Max Bader, and Mark Fisher. All right. So what has happened, I think, over the last decade in deep learning and in general in machine learning is that what you see on your left here, there's been massive focus on standard accuracy and improving the accuracy on popular data sets like ImageNet, which are instrumental for a lot of the advances that happen in deep learning. And so what happened is that this accuracy at some point started reaching human-level performance on different tasks. So around the 97 and whatever percent that surpasses what kind of a human would do. But what's happening now is that if you actually take those models into the real world and you try to apply them, use them there, oftentimes some issues arise, and it could be that standard accuracy is just not enough of a metric for building machine learning models. So car fatalities, not being able to recognize children in the machine perception system, or misdiagnosis, picking up the wrong correlation in the data, or unfairness, and so on and so forth. So these issues kind of point to this problem that real-world machine learning requires some form of guarantees in order to deploy it safely. And this has really been the focus of what we've been doing over the last few years at ETH, and hopefully at INSAIT soon, and there are some students starting who are going to be working on this topic. So we're looking at mathematical techniques to build new kinds of machine learning models that come with guarantees, be it deterministic or statistical guarantees, as well as aspects of security. Like in the previous talk, we saw federated learning. So we've been looking at reconstructions from gradients, provable defenses, differential privacy, and a lot of those techniques, including homomorphic, by the way, which is very slow, unfortunately, for large models. But we have actually an upcoming paper combining provable machine learning models with homomorphic encryption. You can check it out. It's coming up in CCS next month. Okay, but today I want to talk a little bit about fairness, just the particular aspects. What I find very interesting about this new space, it's basically a new direction in machine learning. There is a conference now called SATML, is that it's intellectually very interesting as well. It combines different aspects of gradient-based optimization, logic, verification, essentially techniques from like first wave of artificial intelligence, and the second one, so data-driven optimization together with logic, and I'll show you a little bit of that. Some of these combinations are actually quite surprising. And the whole field really has a bunch of sub-areas. It's just growing very rapidly. Okay. So I'm just going to focus on fairness here, just that particular property, because it's kind of easy to illustrate a lot of the techniques. Why is this important, and why is it hard? Why is it important? Well, machine learning models are used increasingly in various settings. So if you want to reason about will a person get a loan, or will a person commit a crime in order to make a prediction, or will they get hired, you may rely on some of these models to make a decision. And the European Commission is increasingly creating all kinds of regulations on fairness bias and data minimization. How many people know about data minimization? Some people, right? So people get fined now, actually millions, for requesting features that you don't need for a machine learning model. And so there is a lot of issues with fairness. For instance, Amazon scrapped a tool that was secretly biasing against women hiring, which is not great to have such biases at all. We want to prevent this and build models that essentially debias the data. Even if the data has bias, we want to not perpetrate this bias for the model. Okay. The first attempt to solve this problem generally is with changing the data. So you can take the data that you have, and you can try to remove some sensitive features in the data, like age or race or gender or whatever. But what can happen is, due to correlations in the data, even if you remove some item, you can actually uncover this item because of correlations. So for instance here, even if you remove race from your data, due to the zip code, the postal code where the person lives, you can figure out that the person is likely of a certain race. So just security by obfuscation, we know it doesn't work, and fairness by obfuscation also doesn't work, and it's quite easy to break. So what actually means to be fair? There are two general paradigms, which are almost like two subsets, two sub-areas. One is called individual fairness, which basically says that if you have two individuals, like me and you, what does it mean for us to be treated fairly? So if you have two individuals, x and x prime, according to some similarity metric d here, the individual fairness says that the model, when applied on x and x prime, are going to make similar decisions on x and x prime, or identical, depending how you define similarity. So you have similarity in the input space, and you have similarity in the output space. And one of the challenges here is to define this metric d. What does it mean for two individuals actually to be similar? So that's a notion of individual fairness, and it's a deterministic notion generally. There is another notion of fairness, which is called group fairness, and it's more probabilistic in nature. And what it does is it requires that the probability that the model, machine learning model, could be a neural network, could be a decision tree, could be a random forest, could be whatever, that the probability that the model assigns to a label coming from different groups, so if you have a sample coming from one group and a sample coming from another group, the probability that the model makes the same decision is similar or identical. And there are many ways to define these groups. And there are many instances of group fairness, like demographic parity, equal opportunity, and many, many more. So these are just the two major branches of defining fairness. Okay, so here are some of the challenges that we want to talk about today. So one is a little bit in the definition, and then we have the enforcement, and then we have how do you actually prove that this is true? How do you prove that the machine learning classifier or the model in general actually does what it's supposed to do, as opposed to just best case guess kind of heuristic? So there are three general paradigms for enforcing individual fairness. We'll talk mostly about individual fairness. We are actively working on both group and individual fairness. For individual fairness, there are generally three paradigms that people use to enforce it, but the leftmost one is kind of the most popular one. So in the leftmost one, what you have is you have input data, and then you do something called representation learning, and you transform this data into some kind of debiased data, and then you can train models downstream. So it's quite a modular setting, quite desirable, because you separate the training of the client classifiers, or whatever models you use, from how you produce the unbiased data. You can also do in-processing over here, just take the data and do something in the model, but that's very, you have to change the model now, which is not so great. And you also can do post-processing, which is once you get a prediction, unfair prediction, you can try to make it fair. But by far, this is the model on the left, where you are trying to get more of a modular reasoning situation. So I'm going to talk a bit about this, and I'm going to show you on these techniques on two kinds of data. One is on tabular data, which is a mixture of categorical features and numerical features, like this example here with the age, salary, loan, whether somebody got approved for a loan or not. That's an example of low-dimensional data, where we're going to be obtaining deterministic proofs, mathematical proofs on the classifiers. That's a work that appeared at NeurIPS 2020. And the other one that we'll briefly talk about is work that's about to appear in ETH, where we are enforcing fairness, building machine learning fair classifiers for high-dimensional image data. And here you're going to obtain statistical proofs. So both have guarantees, but just of a different kind. Okay, so let's look at that a bit. And how the pipeline looks if you want to build machine learning classifiers that are fair in this representation learning setting. So don't worry about this picture. We're going to explain it in a second. You have generally 3 participants in this space. One is the data regulator, which says what is fair, what is similar, excuse me. One is the data producer, which produces the debiased data. And one is the downstream classifiers, of which can be many. So let's look at them. So there is a bit of a math here, but we'll explain it. So if you look at the data producer here, so what we have in this picture here is we have an input x, and we have some definition for what does it mean to be similar to x, captured by this formula phi. So this formula phi is true when x prime is similar to x and false otherwise. And so what this data producer does is it takes this region around x, which captures the points that are similar to x. And as you can see, this is a non-convex region. And then what it does is it has an encoder here, as you would expect, which tries to map all these similar points close by in the latent space. So that's what this says here. So if they're similar, try to map their representation z and z prime, according to some norm, L2 norm here, close in latent space. So then you'd end up with something like this funny non-convex shape over here. Make sense? Okay? And so you train this network like this. The data producer will train it to try to map them close in latent space, over here like this. But that's a non-convex shape. So it's hard to work in certification with non-convex shapes for many reasons. And then what the producer does is it takes this non-convex shape and it bounds it in some convex shape. In this case, it's a bounding box. Here is just 2 dimensions, z1 and z2, but it computes a bounding box, which bounds this box. And the guarantee of this bounding box is that anything which is similar to x is going to be included in the bounding box around z, around the encoding of x. Okay? And then once you have this box, you actually have achieved modularity, because now you can take any downstream classifier. Essentially, you have a new data set for every point here. You have a new data set here. You have a new point here, formed of the encoding of that data point and the epsilon around it, what's similar to it. Based on this information, you can now train your downstream classifier here, the data consumer, to do what it does, classify the data according to some label that you want. And you can also prove that anything in this bounding box here classifies to the same thing. So you have this modular reasoning. So let's unravel this a bit. Okay. So the first part is defining the notion of similarity. So this phi function here. Okay, so this phi function obviously induces a set of similar points. All right. So here is an example of a phi function, of the phi formula. It's a mixture of categorical and numerical variables. So what it does is, I have 2 points, x and x prime. So for instance, this could be Bob, like this point here. Bob is 32 with some income. Pretty good income, right? Not bad. And then we have Alice, which is a bit older and has higher income. And you can define the formula phi to say when is it true, when they're similar. And what this thing says is that they're similar when all their categorical features are the same, except race and gender, and all their numerical features differ by some constant, alpha. Make sense? So you do these definitions, and where are those definitions coming from? You should ask yourself, who's defining those things? So there is a regulator who defines it. An interesting thing we're working on now, we just submitted a paper on Thursday about learning these things from users. So you can do techniques like active learning, crowdsourcing, and so on and so forth to actually learn the formulas from data and from users. So it's quite, I think, interesting and not been done before. But anyway, you define the formula phi, which captures similarity between individuals. And then you are good there. And so what you want to do at the end, what is the optimization problem you want to solve? Because you have to train these classifiers somehow, or these models. So don't worry about this expression here, we'll just explain it now. It's actually quite intuitive. So what it says is that the goal is to train a classifier M. M is just the composition of the encoder, which takes the point X. And after the point X, after you encode it, you just run the downstream classifier. So this is just the end-to-end pipeline. So it just takes a point X, takes a point in the region around X, which is similar. And then it says I want to maximize when the number of the similar inputs have the same decision by the model. And the same decision by the model or similar decision is captured by this mu, which takes the two decisions of the model on the 2 points and tells you whether it's true or not. Okay? And how you define it, that could be a quality, that could be whatever you want. So that's what this does. And of course, if you don't know about expectations and random variables, you can just imagine that it's a data set. You pick a point X, you have the region around X, and you sample points to instantiate the quantifier. And then you solve the expectation. Okay? And so what's nice here, you can plug in any kind of, as I mentioned, any kind of classifier here downstream. So let's understand how we would actually do this technically. And that's actually very interesting because it involves a combination of logic and differentiable logic and machine learning. And essentially generalizes adversarial training, as some of you may have heard. So what you want to do is remember what the encoder wants to enforce. It wants to say that if 2 points are similar, come here, my friend. Yeah, come. So it says if 2 points are similar, then they should be mapped close in the latent space. That's what it says. But how would you do this? How would you enforce this logical constraint in a machine learning model? What are you going to do? This is like logic, right? And that thing works with data, differentiable reasoning, gradient descent, or whatever. And so there is something that's interesting that we did in ICML 2019, which is called DL2, like deep learning plus logic. And so what it does is it takes formulas like this. So this is implication here, which is just the negation and the union and the disjunction. And then what it does is it translates a formula like this. This paper tells you how to do it. Translates a formula like this into a loss function. So it takes a formula and translates it to a function. And then once it translates it to a loss, you can actually use it in your normal gradient optimization. So it's quite nice. So this is part of the translation. For instance, implication, you translate to the negation, because implication is just the negation of phi, disjunction omega, right? So here is what we have phi. Here we have some expression omega. And so you do this recursive translation downstream, and you just end up with some mathematical expression. Obviously, this would have to be without quantifiers. If you have quantifiers, then it becomes different. Okay? So just to give intuition what the translation does, what it does is it takes a formula on the left, like the one we looked at. So what you see here, it's a convex shape which captures the satisfying assignment of a bunch of constraints, these lines here, these colorful lines that you see in 2 dimensions. So it's just lines. And you just take their intersection. And the intersection of these lines is the points where the formula holds. So obviously, you're less than this line, greater than this line, less than this line, and so on and so forth. Okay, so some inequality constraints in 2 dimensions. This is actually octagonal shape. It's known as the octagon relaxation. So now, this is a logical formula. And now this logical formula, you can use those translations to convert it into a loss function. But what does this mean? What it means that this theorem here, it says that wherever the formula is true, the loss is 0, and wherever the loss is 0, the formula is sat. So what it is really is essentially a differentiable SAT solver. You can think of it this way, or generalized SAT. So you can do machine learning and for SAT. Right. So you cannot prove, but you can find counterexamples, find satisfying assignments. Okay, so that's just an intuition about the translation. And how would you still do this? I mean, how would I enforce these constraints into my encoder, into the resulting model? Like how would I map these points that are similar together in the latent space? And so what you do is something that I quite like. This is essentially a generalization of adversarial training to logic, because adversarial training just is hard-coded to a particular spec, adversarial examples. But here you have arbitrary constraints, essentially quantifier-free. And so what it does is something very simple. It says what you should do. You should find the worst-case behavior of this. Try to find an example. So you have X. Find the point here in the similarity region, such that you make you try to enforce the bad case behavior of the formula. So try to find essentially the largest violation. So do that. Find this X prime, X star. So that's like the worst case behavior. So you're trying to enforce here the negation of what you actually want. So try to find like the worst case behavior of this formula. And then what you do is you come here, then you take that point, and you say, find weights in the encoder, which minimize the effect of the worst case behavior. So this is how adversarial training works. Usually nested optimization, min-max or min-min optimization, which are hard problems to solve. You linearize the inner problem, and then you find the worst case behavior. And once you find this worst case point that makes the model do bad things, you try to figure out weights that minimize it. And that's what this does. Okay, so this is just adversarial training, but lifted to logic. Okay, so we have that. So this is this part of the pipeline over here. So you popping up, you had a point, you have a region around it, formula phi that defines similar points. And then you encode those points. You train this encoder using what we just showed, generalized adversarial training. And then you'd end up with some kind of a non-convex region. But still, it's not guaranteed, because this is just best case training. There's no guarantees that all the points would actually map, that delta close in the latent space. And so what you want to do, once you have done this lifted adversarial training, you want to do the second step, which is, let me go back here, which is computing this bounding box. So we're going to spend less time on this, because this is really its own business. And if you want to know more how to do this, you can come to the tutorials. But essentially what happens is that you want to take the encodings here, and you want to find the bounding box. And the way that you do this is the region here that you got induced, is that you're going to encode the whole thing in a mixed integer linear programming problem solver. Okay? And then once you encode it, you're going to find the epsilon that bounds the worst case distance from Z. So this is, the encoding is fairly direct, and you get these bounding boxes now. So you use the generalized adversarial training to do your best case effort to map similar points close in latent space. And once you have that, you can, around the point Z, compute your sound bounding box. At that point, you have absolute guarantee that anything inside this, anything similar to X is guaranteed to be epsilon distance from its representation. Somebody can say, why am I actually needing the first step to do the encoding? But if you don't do that, you're going to get very large boxes, obviously, because it's not biased for this task. So that's the first part of what happens. In the second part here is once you already have the encoding of the point here and the bounding box, so you have the Z, you have the epsilon around it. That's captured by some bow. Okay? And then what you do is you now are the classifier, you are the user of this representation. So now you can do whatever you want here. You can train your classifier with adversarial training, with normal training, in order to get a final solution, and then prove it using mixed integer linear programming again, or some other mechanism that scales, whatever mechanism you want. So essentially what would happen is that you would prove that any point here is classified to the same thing. Of course, you cannot enumerate, because this is either infinite or unbounded or very large and bounded, so it's impossible to enumerate points. But you can use these techniques from verification to prove what you want. Of course, you may not be able to prove it, and the region may cross the red boundary, the decision boundary, in which case you will not be able to give a guarantee. You'd say, I cannot prove it. So if I have, imagine this, I have like 1,000 points in my test set, I may be able to do this for 700 of the points, so I have 70% fairness guarantee, right? So adversarial training gives you upper bounds, certification gives you lower bounds, and you always try to kind of bring them together, hopefully by not lowering the upper bound. Okay, so this gives you a bit of an idea, hopefully, what happens here in this pipeline. And what we saw, interestingly here, is that you have training, you have logic, you have combinations of training and logic, and you have verification. And you can plug in your favorite verifiers here that you want. Okay, so this is for tabular data. But one of the fundamental problems is how, again, you define this notion of similarity. So in verification, we know that the effectiveness of a verification method heavily depends on the spec. Because verification to scale, you need to forget things. And how would you know what to forget if you don't have a spec? So now the question is, can you actually do this kind of techniques for image data or natural language processing data, to where you have similar treatment? So, right? So if you have something like, if you have something like, come back. If you have something like this, some pictures, you can say, what happens if I want to be fair with respect to changing the hair color, or changing the eyes, or putting makeup, okay? So how would you actually do these specifications? It's not really possible to do this specification on the input space, on the pixel space. You need to have a way to define these specs somehow. So clearly there is some generative model involved. And so this is this pipeline here that I will tell you a bit. This is going to be much faster because we don't have so much time to discuss. If you want to know more, you can look at the paper or you can listen to the talk. This month already, it's October. So the idea is actually quite similar to what I told you before. You have a point X, which is a picture of a person. You take that picture of a person, and then you would encode that picture in the latent space of an encoder. In this case, we use a glow encoder. It's a model which is invertible, so that you can go back from the latent space into the input space and see what changes you made to the latent space, and you can interpret it. Now you take the point and you go to the latent space. But so what that you go to the latent space? You need to essentially define a specification on the latent space, because you can modify the latent space to change the hair color or the eyes or whatnot. But so what? I mean, this doesn't give guarantees. I can change and get different pictures. And then you have this technique here, which is similar to the one before, but just in spirit, but technically it's quite different. And essentially what it says is, these changes to the latent space that you're interested in, like changing of the hair color, they get mapped provably, mathematically provably, close to each other within some radius. So again, we have this like z epsilon. Now we have here something else like this. So again, you're going to learn a representation here of this specification. So essentially what you're doing is you are learning representations of the specs, okay, that you are going to then take and do exactly the same thing we did before. We're going to take this region, okay, which is guaranteed. Here's some guarantee that, everything here in the specification gets mapped epsilon close. Statistical guarantee. And then what we're going to do is, obviously, if we prove some radius which is greater than what we had here, we can ensure soundness, and that things map to the same point. So let me just mathematically define it. So we use the generative model in the latent space to find images which are similar to each other. So you have the point ZG, which is the encoding of X, and then you can change it using some vector alpha. We're not going to talk about what alpha is, how you actually change it. With the magnitude or the direction of the vector changes different properties of the picture, like the hair, the eyes, or whatever. So that's your definition of similarity. Okay. And then in the second step over here, which is really where the innovation happens, is use something called center smoothing. So smoothing, randomized smoothing, is a recent technique that came out of differential privacy, actually. You see how the fields are connected in some sense, which is kind of unexpected. It's a statistical technique which can handle very large models, like arbitrary large models, because it's based on sampling. It's approximating the integral by sampling, but essentially based on sampling. And what it does is what it says, that the similar individuals here get mapped within some distance ds from each other in the latent space according to some norm. So you end up with this guarantee here. So that's a mathematical guarantee that holds with certain probability and some confidence. Okay? And then once you have this, you're basically done. You can use it in a downstream classifier. So you can then take your favorite randomized smoothing or deterministic certification technique, and you can prove that everything in this orange circle here classifies to the same label with some confidence. And that's what this said. If you have a classifier you are given, you can produce a smoothed version of that classifier. That's what the hat stands for. Same thing here. Such that, the center point and some delta close to the center point produces the same classification as the center. That's what this does. Okay, so again, this idea of representation learning, but this time kind of instantiated with very different setting. Okay? There is one downside here. You can think what it is. Can somebody think what the downside is? Yes? Loss of accuracy. That's always a downside when you're trying to have multiple objectives, like fairness, robustness, accuracy. There are ways to go around this, but generally that's something that researchers are studying actively. There is a more fundamental downside. Time complexity. Smoothing is actually quite scalable, so that's probably not close. Let's extend. Even in the previous one, there is a bit of a hidden thing I didn't say, is that to get these guarantees, because you always get guarantees in expectation, you need to do this at inference time, which means you may have to take like hundreds, thousands of samples around the point at inference time, which can be expensive. People are working on reducing this overhead, but there is another thing which is even more. So the guarantees are with respect to a given encoder, right? So I have an encoder, but if I give you another encoder, the guarantees will change. Okay. So this is not super ideal. That's something we're working on now. How to actually get away from this. Oopsie. Okay. All right, so I hope this gives you an idea. The code is public. We have all the code here on ETH SRI, all the verification code that's used in competitions, in industry, a lot of projects with industry like Airbus and SBB and others, and all the code is public. So you can just go and take it and run it and improve it, hopefully. What's a natural extension here? Which domain would you extend this to? Huh? Regression, maybe, yes. Domain. You can extend it to NLP data, for instance. But what it means that you need to have an interpretable way to generate specifications in NLP. So if you go to the latent space, you need to have a way to perhaps change the toxicity of a text in the latent space. So this begs the really fundamental question of what are the specifications, how do you get specifications in machine learning, right? Okay, so I hope this was interesting to you. So in conclusion, what we discussed is that fairness is one very important concern when you're talking about provable machine learning models and deploying these machine learning models in the wild. The techniques that I showed you are very general, actually. You can use them for other properties beyond fairness. Individual fairness is very related to robustness, as you can see. These techniques come with mathematical guarantees, statistical or deterministic guarantees. And to get the guarantees, you cannot just do verification. You need to bias the models during training to get these guarantees. Otherwise, you end up with very loose guarantees, and you drop a lot of accuracy. There are different kinds of guarantees, deterministic guarantees and statistical guarantees based on randomized smoothing. If you don't know about these things, you can come on the tutorial to learn a bit about them. There are many, many extensions. You can apply the second techniques for foundational models, large-scale models, if you don't have access even to the model, because you can learn representations, and then the downstream model can be a black box. What are interesting future works that we are looking at? I mentioned to you already, learning the fairness specifications. Right now, the community has hard-coded a bunch of them because we have such a hard time with getting accurate and robust and fair models. We don't understand how to get everything together yet, especially with guarantees. And upper bounds that the community gives, they sound good, but turns out in many cases that they are actually quite loose and incorrect in a sense. So you need lower bounds. An interesting direction that we're looking at is in group fairness. How do you do this for group fairness without knowing the downstream classifier? So I think this is a work we just submitted to iClear, which I think is really a breakthrough work for getting certificates without knowing anything about the downstream classifier, whatever downstream classifier you have. And you can actually generalize this across other modalities, like these techniques that I showed you, that hasn't been looked at yet. And yeah, that's all I had for you. So thank you very much.